Okay, so this is a revision video about topic 2b, which is the second part of forces in motion, or forces, for the Edexcel GCSE 9-1 syllabus. I'm going to try and be quite quick with this, so it's not a full explanation, it's just some key content in case you've got a test coming up or you just want to remind yourself of the topic. So we're going to start with what a force is. A force is a push or a pull. Back, like you said, when you're back in reception, you talk about forces for the first time. It's a push or a pull, and it happens when two bodies interact with each other. They don't need to be touching for this to happen, but it's when two things interact. Now, the unit of the force is the Newton, named after Sir Isaac Newton himself, because he did a lot of work on forces and kind of theorised that they existed. The symbol for that is a capital N. Now, Newton did an awful lot of work on forces, and three really important things to know are his three laws of motion, essentially. And they explain how forces determine how things move. So his first law, Newton's first law, is this. If the resultant force in a body is zero, the body will. Now, I'm going to tell you what the body will do, but firstly, what's the resultant force? Resultant force is the overall or net force on a body. And if there's no resultant force in the body, that means that the forces are balanced, or that the body is in equilibrium, we call it. And when something is in equilibrium, then the body will travel at a constant velocity. Travel at a constant velocity. Now, that could be that if it's stationary, it will stay stationary, and that's the most common experience we have of this. So, for example, right now, this paper is sat on the table and it's staying still because the forces on it are balanced. But if you're traveling at a constant velocity, so for example, if you are driving along the road and you're driving at 30 miles an hour and that is not changing, there is no resultant force on you. The force of friction that's pushing backwards is equal and balanced to the force of the thrust of the engine that's pushing forwards. Now, the reverse of that, therefore, must be true. So if the resultant force in the body is not zero, then it won't travel at a constant velocity, it will change velocity. And changing velocity, which you'll know back from the motion video, is a type of acceleration. So we'll accelerate a rate. There we go, that's better. So the body will accelerate if the resultant force is not zero. Now, that could mean that it changes speed, but it can also mean that it changes direction, because velocity is speed in a given direction. So I've got three situations here, and we're going to think about whether they are balanced or unbalanced and which of Newton's laws which version of this law will apply. So here, the forces on this object are balanced because there's 10 newtons acting in opposite directions. So the resultant force here, or FR I'm going to call it, is equal to 0 newtons. And I worked that out by doing the force in one direction minus the force in the opposite direction. So this body will stay at a constant velocity. Now, if it was already still, it will stay still. If it's already moving, it will keep moving at the same speed in the same direction. This body here, it's unbalanced, these forces. Hopefully that's kind of instinctive to see. Unbalanced. And the resultant force here is going to equal the biggest force minus the smaller force. So it's equal to 10 minus 4, which is equal to 6 newtons. Now, force is a vector, and therefore I need to add in a direction. And the direction will be where the leftover force is, which is this way. So 6 newtons to the left, or I can draw an arrow there. Now, if the forces are unbalanced, this body will accelerate. Now, if it's already still, if it's stationary to start with, it will start to move that way and speed up. If it's already moving that way, it will speed up. If it's moving that way, it will start to slow down. So accelerate can mean speed up or slow down or change direction. Now, this final one tricks people a little bit, because I've got two forces that are equal in size, but they're not balanced. This is unbalanced because they're not in opposite directions. And for forces to balance each other out, you've got to have them in opposite directions. So the resultant force here is not zero. Now, you don't need to know in this section how to work out the resultant force, but you can hopefully work out the direction it would be, and it would be in this direction here. And for those of you who want to know, it would be the square root of 4 squared plus 4 squared. And you can work out what that means if you want to. So the resultant force isn't zero, it's acting upwards, therefore this body will accelerate. It will maybe change direction, it will speed up or slow down, it depends on what its motion is already doing, but it will definitely accelerate. So here are three really common examples, and I've chosen these to try and demonstrate the different names for forces that we use. So if we've got a stationary car, now if the car is stationary, it means it's travelling at a constant velocity of 0. So the forces on it must be balanced. If it's stationary, the engine isn't on, so there isn't a force pushing it forward, therefore there's no force pushing it backwards. So there's just two forces acting. Now the first force that always acts on these objects is weight. And we label that with a W. That's the pull of gravity on the object's mass. We call it weight, not gravity. And generally, I always draw my force diagrams, and they're seen most this way, with the arrows coming from the centre of the object, not going into the object. Now, if this car is stationary, the forces must be balanced. Therefore, the weight must be balanced with something else, and it is. It's balanced with an upward force, and this force is called many things. I generally call it reaction. Or you can call it the normal force or the normal contact force. And it's called the normal force because normal means perpendicular, and this force is always perpendicular to the surface. So it's the reaction force of the road pushing the car up. These two arrows must be in opposite directions and must be the same size as each other. Now here I've got a boat travelling at constant speed, so once again the forces are balanced, but this time if it's travelling at a speed there must be a force pushing it forwards, which I'm going to call the thrust of the engine or the engine force. Now there must be a force balancing that out if it's travelling at a constant speed, and that force will be a combination of lots of different types of friction. There'll be air resistance, there'll be water resistance, so we can put them all together in something called drag. It's like an umbrella term. The boat still has weight. It's not made of nothing. But here, instead of calling it reaction to balance that out, we call the force from the water upthrust. I'm just going to fill those in. So quite common that people use this for different things. It's only really used at GCSE for liquids in water. And then we've got an aeroplane taking off. And by taking off, I mean that it's accelerating because it's getting faster and changing direction. So this aeroplane will have four forces acting on it. It will still have weight acting on it because it's an object. And there'll be an engine force acting on it too. And that'll be pushing it forwards. Now, if it's going to take off in this direction, there must be an overall force which is acting kind of upwards this way. So there's a force more than balancing out the weight. It's bigger than the weight. And that force here for an aeroplane, which should be bigger than that, sorry. Let me just make that larger. There we go, it must be longer than this force here, is called lift. Okay, so because the aeroplane isn't touching the ground, it's not got any reaction force, it's lift when it's in the air. And then there'll be frictional forces, such as drag, pulling the plane back. But as long as these two forces are bigger than these two forces, it means the forces are unbalanced. And we care about the pairs in opposition. So that's Newton's first law, and it's only taken me 7 minutes, so my hopes for a half-hour video may soon be dashed. Newton's second law is summed up in this equation here. F equals ma, or force equals mass times acceleration. Now we've come across all of these things before, so I'll just quickly write the unit. So it's m/s squared for acceleration. The unit of mass is the kilogram, not the gram and not the newton, and the unit of force is the newton. Now there's a couple of things to unpick from this, including a core practical. The first thing to have a look at is something called inertial mass. Now inertial mass is one of those terms, you just need to learn it for the exam. It's how difficult it is to change the velocity of an object. So think about a shopping trolley. If it's empty, it hasn't got a lot of mass in it, it's really easy to push it and make it start moving and make it stop. If you fill it up with lots of food, it's actually quite hard to stop it moving or hard to start it moving, so it has a higher inertial mass. And we can also define it as the ratio of force over acceleration. So we can rearrange this equation for m equals F over a. So a slightly easier way to remember it is that inertial mass is force divided by acceleration. And that kind of brings us on to this special case of weight. So weight and mass are not the same thing. So weight does not equal mass. They're used interchangeably in the English language, but that's wrong. In physics, weight is a different thing to mass. They're very, very much related to each other though. Now the special case is when we have the force of weight, W, instead of F, it equals mass times the acceleration due to gravity, because weight is the pull of gravity down on the mass of an object. And acceleration due to gravity has got the symbol g. So we have W equals mg, which is just a sub-equation really for F equals ma. Now on Earth, g equals 10 newtons per kilogram, or we can also write it as 10 meters per second squared back when we looked at acceleration in motion. The newtons per kilogram comes because if you rearrange this equation, weight divided by mass, it's newtons over kilograms. On the moon, it's much, much smaller than that. G on the moon is 1.6 newtons per kilogram. So gravitational field strength, which is the same as acceleration due to gravity, but it's just a different name for it, varies from planet to planet. And the bigger the planet, generally, the bigger the gravitational field strength. So on Jupiter, it's much, much bigger than 10. So W equals mg, a really easy way to work out going from mass to weight is just to multiply everything by 10, as long as your mass is in kilograms. It must be in kilograms. You need to convert from grams. If not, because then the weight will be in newtons. So for example, a 1 kilogram book weighs 10 newtons. A 5 kilogram book weighs 50 newtons. Now, if I was an astronaut and I went to the moon, my mass would stay the same. No matter where I was on the Earth or the moon, it would be X number of kilograms. However, my weight would be smaller on the moon than it is on Earth. So your weight is what it is on Earth. So let's say we've got an astronaut that's 50 kilograms. On Earth, the weight would be 500 newtons, but on the moon, I've stupidly done this without thinking what the actual answer is, it would be 50 plus 30, 80, I think, 80 newtons. Please don't comment if you think I've got that wrong, just work it out for yourself. So your weight will decrease if you go to the moon, even though your mass does not change. The final thing to have a look at here is the core practical that you need to know about for this equation for Newton's second law. And the core practical is the one that I do is looking at the relationship between acceleration and mass. And to do that, we need to keep force constant. So that's with a constant force. Now you could, in exams, see it any way around, maybe looking at if you keep the acceleration constant, what's the relationship between force and mass. But this one I'm going to look at is if you keep force constant. Now, if I keep force constant and rearrange this equation, so acceleration equals something, I get acceleration equals force divided by mass, which is where I've got this relationship. The acceleration is proportional to 1 over mass. That's inversely proportional. And if I draw that on a graph, it would look like this. Have a think about what y equals 1 over x looks like as a graph in maths. And you might need to prove that using an experiment. And this is the stand-up setup for that experiment. So what I've got is I've got a trolley that's attached by a string over a pulley to some weights or masses. And those masses / weights, they're masses that provide weight, will provide a force downwards, which is the weight of the masses. This is your force, and you keep that the same. In this version, you keep that constant. There are versions where you increase that and keep something else the same. The pulley transfers that force acting downwards and makes it act along the string. So whatever mass you put on here is going to be your weight when you multiply it by 10, and that stays constant. Now the trolley will accelerate, it will speed up as it goes between these two light gates. Okay, so these are light gates. And the trolley will accelerate as it travels down the slope. And I'll talk about what the slope's there for in a moment. So as it goes through the first light gate and the second light gate, the speeds will be different. So this will be the initial speed, u, and this will be the final speed, v. If you measure the distance, x, between these two light gates, you can then use the equation v squared minus u squared equals 2ax to determine the acceleration. So acceleration equals v squared minus u squared over 2x. And if you want to look at the relationship between acceleration and mass, you work out the mass of the trolley, you do this experiment and you work out the acceleration, and then you add masses onto the trolley one by one and you increase the mass. So you vary the mass, see what happens to the acceleration. So you've got F equals ma. We're going to keep F constant, we're going to increase the mass, and we should see that the acceleration decreases because of that. Now the reason for these books here, they're meant to be textbooks. This is something called friction compensating, and it's asked about quite a lot in the exam. Now, if you had a flat ramp with the pulley, these weights might not always pull the trolley because friction gets in the way. So what we do is we friction compensate, and you prop up the ramp until the trolley just starts to move on its own. When it just starts to move on its own, that's the level at which the slope of the ramp has kind of compensated for the friction of the ramp. So you do that before the experiment and then keep it constant for all of the different repeats. Right, Newton's third law is actually my favourite, which is really sad, but a lot of people hate it. And it's if body A exerts a force on body B exerts an equal and opposite force on body A. But it's more famously known as every action has an equal and opposite reaction. And it's quite hard to unpack. Now, this causes something called action-reaction pairs. Every single force that arises in a pair with another force. And these two forces must be the same size or equal in size or magnitude. They must be in opposite directions, not different directions, opposite directions. And these are the two that everyone remembers because they're in the definition. But they also need to be the same type of force, and they need to act on opposite or different objects. So we can see here that the force of body A acts on B and then B acts on A. One force acts on A, one force acts on B. They're equal and opposite, but they must be the same type. That's kind of missed out here. So here's an example of a typical problem that people get quite confused by. I've got here a book, and that book will push down on the table with a weight of 20 newtons if the mass is 2 kilograms. And people then automatically say, okay, well, that's going to be counteracted with an action-reaction pair of the reaction force, which will also equal 20 newtons. Half that's right, half that's wrong. This is called a free body diagram. But this is not an action-reaction pair. Let's think about why that is. So I've got two forces of the same size, tick, the opposite direction, tick, same type of force. Well, weight is a force of gravity. Reaction is a push-up from a table, not the same type of force. Act on different objects. The way it acts in the book, the reaction acts in the book. Doesn't work. So this is not an action-reaction pair. There's actually two action-reaction pairs going on here. We're going to start with the reaction force because it's a bit easier. So there's a reaction force of 20 newtons acting upwards. This is the table pushing up on the book. The pair for that is downwards 20 newtons, and I'm going to switch the objects around. It's the book pushing, same force, it's a push force, opposite direction, down on opposite object, table. So I just kind of take the sentence and then flip it round. So the table pushing up on the book is paired by the book pushing down on the table. And you can do this yourself. If you push down on your table now, you can feel the table pushes back with the same force, and that's an action-reaction pair. The weight one's a bit harder, okay? So we've got weight here of 20 newtons. Now this is the pull of the Earth's gravity down on the book. Now that must be counteracted, this is on the Earth, with a force the opposite way, the opposite direction, but the same size. And this one here is the pull of the book's gravity, random capital letter, up on the Earth. So I've done the same thing. I've switched those objects around. Earth and book have switched around. I've changed the direction down and up, but I've kept the force words pull and gravity the same. And you do this, okay? The earth pulls down on you with your weight and you pull the earth back. If you jump, the earth does come towards you very, very slightly, but you come more towards the earth. The reason we don't notice it is because A, we're not the earth, so we can't feel it. We can only feel what's happening to ourselves. And also, you're a lot smaller than the earth, therefore your acceleration is much bigger than the earth's. So we don't notice it because the earth reacts so little. But the Newton's third law does hold. Now these laws have got some consequences. So the first is circular motion. This is a bit of an extension of Newton's second law, I suppose. And circular motion tells us that if an object travels at a constant speed in a circular path, it's quite hard to read that word, it's accelerating, which requires a resultant force. Now, why is it accelerating? Well, it's travelling in a circular direction, which means it's changing direction, and therefore it's changing velocity. And remember, acceleration is the rate of change of velocity. So if you change velocity, you are accelerating. Now, anything that's accelerating requires a resultant force because of F equals ma. To have a non-zero acceleration, I need to have a non-zero force. Now, this resultant force in this circumstance is called the centripetal force. And there's always a force acting as this. It's not an extra force, it's just that one force acts as a centripetal force. And this centripetal force must always be towards the centre of the circle. Now, an example here is the moon going around the Earth. Okay, so as the moon travels around the Earth in this direction, its velocity is acting this way. Now, the moon is over on this side. It's travelling this way, the velocity will be acting this way. So the velocity is always, we'd say, tangential. It makes a tangent to the circle. Then the centripetal force has to act towards the centre of the circle. So the centripetal force acts inwards. I'm going to call it FC, centripetal. And you can notice that it's always a right angle between the velocity and the centripetal force. Now that centripetal force has to be something, and in this example, the centripetal force is gravity. We know that it's gravity that causes the moon to orbit around the Earth. The same for the Earth going around the sun. Any satellites travelling around a planet, it's always gravity. But there are other examples as well, and there's some simple ones that you probably haven't thought about. For example, in a washing machine. So in a washing machine, the objects spin round in the drum, and the reaction force of the drum pushes the clothes into the centre. A roller coaster with a loop-to-loop, same kind of thing. The track pushes things in. If you've got, there's quite a few in fairgrounds, if you've got those swings where I'm going to try and draw one terribly right now. There we go, and this is the swings. Those swings are pushing towards the centre. This is a bit more complicated because it's a component of the tension in the chains, but there's always a force acting towards the centre. Anytime you have something going in a circle, we get this thing of circular motion. The next kind of consequence of Newton's laws, and this is Newton's third law, is about momentum, and specifically about the conservation of momentum. But to start with, we're going to think about what momentum is. So momentum is defined as mass times velocity. That's its definition. And it gives us the equation P equals mv. Now, P is a symbol for momentum. We can't use m because that's being used for mass. And we know the unit of mass is the kilogram, and the unit of velocity is the kilogram. No, it's not. It's the metre per second. I'm jumping ahead of myself. Now, these two are multiplied together, which makes the unit of momentum the kilogram metre per second. This is just basically a measure of how much damage something can do. That's how I used to think about it in a collision, but that's not the definition. There's many other things as well. But the higher the mass or the higher the velocity, the more damage it will do in a collision. Think about it. If you had to be run over, would you rather be run over by a massive lorry or a little mini? Well, probably the mini because it's got a lower mass. Or maybe the lorry is not travelling very quickly and the mini is going really fast, then maybe you want to be hit by the lorry. It depends. You probably don't want to be hit at all. It's quite macabre, my version there. Now, usually there's two things to know about momentum. There's the conservation of momentum and there's the change of momentum. Now, this is the principle. The conservation of momentum principle is that the total momentum before a collision is equal to the total momentum after the collision. And I've written P there because I haven't got enough space. But we use this quite a lot in questions that look like this, where you've got two objects that are travelling towards each other, or maybe one stationary, the one's travelling towards it, and then they collide and they either bounce off each other or they might stick and move on together. Common examples are in snooker tables, or thinking about like you might have two train carriages and one hits the other. There's quite a lot of variations that they do. Now, the total momentum before the collision, we have to think about the momentum from both objects. We could write this as a very generic way of writing this equation. And the momentum from object 1 would be m1 u1. And then here, we're going to add it to m2. And u2 is in the opposite direction, so it's going to be negative, and that's important. This is velocity. So times by u2. So here this will come out as m1 u1 minus m2 u2. If they were both going in the same direction, then it'd be a plus. But you have to be careful about this minus sign, you take it into account. And that's going to equal momentum after. Now on this side, v1's now going that way, so this one's negative. So it's going to equal m1 times minus v1 plus m2 v2, or we could say minus m1 v1 plus m2 v2. Now these could stick together, and in that case it'd have the same velocity, but it depends on the problem. Another common problem though is one where you have an explosion of sorts. So here is a cannon. Explosions are a bit funny because the momentum before, and I often write this as the sum of the momentum before equals the sum of the momentum after. If you've got a cannon and a cannonball, before it goes, it has no momentum because it's still. So the momentum before equals 0. So how do we have momentum after? Because we have to conserve it. Well, here, the cannonball, so the momentum of the ball, the mass of the ball times the velocity of the ball, must, if I add it to the cannon, equals 0. Now, if adding it to the cannon, the thing here is that the cannon's going backwards. So we have the MB VC, and that'll be a minus sign. So we essentially get the MBVB, that should be a C, sorry, equals minus MCVC. So they will have, the cannon and the cannonball will have the identical momentum, but they'll be in opposite directions, so they'll cancel each other out. This is much easier to understand with a problem. It's quite hard to do it theoretically, so apologies for the quite garbled explanation. The other thing we need to know about is the change in momentum. Now the change in momentum, and we can write that as delta P, change in momentum, equals the final momentum minus the initial momentum. And we can write that as mv, where v is the final speed, minus mu, where u is the initial speed. Now, there's a formula that has this in it, and this is given to you in the exam. You get given the formula F equals mv minus mu over t. So you don't need to remember this, but you need to be able to use it. And for me, the most useful way of using this, if we rearrange it to write mv minus mu equals ft, the change in momentum equals force times time. Now, why is that useful? Well, a really common way to think about this is in car crashes. Now, think about a car crash, okay? Now, imagine a car crash where there's no airbag, where there's no crumple zone, where there's no seatbelt. If you're travelling at 30 miles an hour and then you suddenly crash, your change in momentum goes from 30 times whatever the mass of the car is to 0. So your change in momentum, no matter what it is, will be the same. If you stop suddenly or if you stop slowly, you still have the same change in momentum. The thing that changes if you have an airbag, so this is with an airbag or with a crumple zone or with a seatbelt, they all have the same thing in mind. They want to increase the time that it takes for you to stop, for you to crash into the windscreen or for the car to stop. So if you've got an airbag or a crumple zone or a seatbelt, compared to not having one, the crash will happen in a longer time. You're going to increase the time of the crash. Now that, if the change in momentum doesn't change no matter how quickly or slowly you crash, means that if you increase the time, you must decrease the force during the collision. And that kind of makes sense. An airbag, we know, cushions someone, so it decreases the force on them. Now, why is that important? Well, forces cause injury. So all of these, they decrease the time. No, sorry, completely wrong. Increase the time of collision to decrease the force. Therefore, there's less injury. Now, why is that? Well, A, we might just kind of realise that anyway, but think about the equation F equals ma, okay? The mass of your car, the mass of the thing that's crashing doesn't change no matter what the force is. But if I've decreased the force, I've also decreased the acceleration or the deceleration. And this small deceleration, so because there's a smaller deceleration, you're stopping over a longer period of time. It means you get less chance of being injured. Think about if you've ever been in a car with an emergency stop, if someone slams the brakes on, you can really feel that you are stopping quickly. You can feel the force on you, it's bigger. Whereas if you slow down when you see a traffic light and it's a nice calm stop, you barely feel the stopping. These two are both things that are much easier to look at in terms of problems. They're harder to talk about theoretically. But that does bring us on to our final kind of section. It's a bit more of road safety, and this is the idea of stopping distance. Now, the stopping distance of a car depends on two things. It depends on the thinking distance of the car plus the braking distance. Now, the thinking distance is how far the car travels, or whatever vehicle, while driver is reacting to stimulus. So let's say you see a dog on the road and you slam the brakes on. The time it takes for you to realise, oh, there's a dog, and for you to move your foot to the brake is the thinking distance, because you'll still be travelling at that point in time. The braking distance is how long it takes the car to stop, or how far the car takes, or how far, I should say, the car travels while the brakes are applied, because they don't work straight away. They have to gradually slow the car down. Now, these two things have different factors that can affect them. So the thinking distance is generally affected by the driver's reactions, or the driver's reaction time. I'm getting sloppy because it's been a long video. Now, this can be increased, the reaction time, by being drunk, so by alcohol. That's why you can't drink and drive, by some drugs, and by distractions, such as, using your mobile phone, or if you've got, kids in the back arguing, that might stop you reacting as quickly. So if you increase the reaction time, you're going to increase the thinking distance. It's also increased by speed of the car. So if the car is travelling quickly, it will travel further while you're reacting than if it's travelling slowly. It can be decreased. It decreases if you shorten your reaction time. Things like caffeine. I'm not saying always drink coffee before you drive, or being awake and alert, which is why you should be awake and alert while you're driving, because you want it to be as short as possible. Now, we can work out reaction time using this little experiment here. It's quite a common one. You've got a ruler. You have a friend hold the ruler above your hand. You have your hand in a palm like so. And then they drop the ruler without telling you, and you have to catch the ruler as quick as you can. And the distance that it drops in that time, you can find a graph that looks something like this. You can find it in your textbook or on the internet, and you can work out the distance that the ruler dropped versus the time, and you kind of read up, and this is your reaction time. Now, the average human reaction time is approximately 0.2 seconds normally, but it will get higher or lower if you're tired, if you're awake, if you're on drugs, if you're having alcohol, if you're being distracted. Now, the braking distance is affected by the kind of physical conditions. Now, they include speed and mass of the car, so the momentum of the car. The higher the speed, the longer the distance. The higher the mass, the longer the distance. So speed is actually in both of these. So speed affects stopping distance overall, which is why we have speed limits in places like school zones, because it means that the brake stopping distance is much, much shorter. It's also affected by the conditions of the road, or your tyres, or your brakes. So, for example, if it's icy, or if it's wet, then there's less friction. And that will cause a longer braking distance, or if your tyres are worn down, if your brakes are worn down. Conversely, if you've got really good tyres or if you're on a very rough road, that will decrease the braking distance. So generally conditions of the car, either its speed or its mass, or the conditions of the kind of the elements that are involved in braking are important. Now there's one more thing to kind of add on to this, and this links a bit to an energy topic. We can work out the braking distance, so we can calculate the braking distance. And you may not have learnt this yet because you need to know about energy to learn it. But when we brake, we have to lose kinetic energy. So the KE lost when you're stopping has to go somewhere, and it goes to the work done by the brakes. Now, if this makes no sense, you'll probably get taught it in the future. Now, KE lost will equal 1/2 mv squared. The equation for kinetic energy is 1/2 mv squared, and the equation for work done is force times distance. Now, this is the braking force, or the force that the brakes can apply, and this is the braking distance. So if you know the initial speed of the car and how much the car weighs, or what the mass of the car is, and the braking force, and you can work out how far it's going to take to stop. And this kind of links back once again to speed. The higher the speed, the higher the braking distance. And because this is squared, it's quite a big change. So going from 20 to 30 miles an hour more than doubles the braking distance, which is why they have those 20-mile-an-hour zones near schools. So in case a child runs out of the road, there's more chance that the driver can stop in time. Now, that was very long. I tried to keep it short, 36 minutes for this one. So if you add that onto the motion, that's 1 hour for a topic, but there we are. Hopefully it was helpful. Apologies for any garbling and for bad spelling. See you for another video soon.